Okay, further flame test. This is your post-lab discussion. So you guys went in there and you combined your chlorides together and you recorded down what color they were when you mixed them together. You also went in there and you mixed all the colors together and you recorded what color the overall flame was. All right. So question number one, it's your opinion on which color was seen more predominant than the others. Also, that predominant color, does that respond to high reactivity? If so, place the chemicals in order of the reactivity. Question number three, I want you to rate those chemicals in order of reactivity according to the activity series of metals. Okay, and you'll find that in the state materials. 4, according to the two lists, does the predominance of a flame test color provide an accurate way of ranking reactivity? So can you use your flame test in order to determine reactivity of a metal? Why or why not? Would flame testing be a good way to distinguish between mixtures of different chemicals? Explain. That's really your opinion based on what you saw and what you went through. Would you use it for that? Question number 6, compare flame tests to individual chemicals rather than mixtures. Did any of the chemicals change their characteristics or flame color when they were mixed with other chemicals? So you did the flame test before, you did the flame test after. Was there any difference between those two, or were they the same? So this also reviews back over your EMF spectrum. And again, we're looking at your visible spectrum. We know that when we excite them, we're seeing them give off energy, and we know that the reds are going to represent lower energy compared to the blue spectrum. Also with this, we talked about how the information about what the star systems look like around us is based on spectroscopy. We get that material in from the spectroscopes, and then we get a readout, and we're able to identify the elements. And that is an application of what you're doing in lab. This also relates back to your classical and quantum theory. And classical, we talked about the fact that light was considered to always continuously give off energy, and that it was like if you were looking at it, it would be like a rainbow continuous spectrum. And in a quantum model, you have discrete packets of energy, which are those bands of light you see with the spectroscope. And it's based on the frequency of the light. Okay. We also talked about Planck's constant. We talked about his theory model with the quanta and the quantum model, and also about the equation. That's relationship, his constant with the frequency gives us the energy of that photon. We also talked about black body radiation. So that's an old concept that was with your atomic history research project. And the idea was that since energy is going to be given off exponentially, that if you were standing next to a fire, you would die. But obviously that's not true because we all live standing next to our Bunsen burners. And so Planck's theory brings that equation back down and explains why black bodies burn red when they're heated, such as your ring on your ring stand. And I also give you the image of absorption versus emission, just giving you that image that if we hit that electron with the right amount of energy, as we saw in our demo, then that electron is going to get excited. Either it's jumping out to another ring as it absorbs energy, or as it's coming down a ring, it's releasing energy to get down. So it also reminds us that with your spectroscopy, we are looking at absorption and emission, and just they're the same readout. It's just one has a dark background on it, and the other one has a continuous spectrum with lines missing in it. So just reminding you of some of your physics vocab there. You have the idea of transmission, and with light, you get a reflection or scattering of light, and that can factor into your result. We also talked about how the little front piece of your spectroscope is basically a bunch of prisms together, and that's why we're able to split them into their respective lines. We also mentioned Bohr's model. Again, that goes back to your atomic history project. And this was some of the results that he was showing, what he was explaining why that he was getting the lines that he got with the hydrogen atom, and explained how they moved in the rings. We also talked about the particle wave duality theory, and we talked about how they did their famous experiment, and they were sending a beam through a thin slit, and when they looked, they realized they had a wave pattern, not a particle pattern. And it also brings into the idea of diffraction, another property of waves that you see when you're working with this lab. Which spawns us into what we're working, which is electron configuration. That's where we're moving to next, where you're actually going to be writing out the configurations for your elements. So such as hydrogen, which is 1s2 because it's on the first row, and it's the second block, and it's actually 1s1. Whereas helium is also on the first block, but it's 2n, so it's 1s2. Configuration just gives us more information about the element. It also tells us about the structure. So an S block is going to be spherical. P block we talked about was going to be dumbbells, X, Y, and Z. D is double dumbbells and donuts. And F is way more complex. But again, we're looking at all your directions, which is X, Y, and Z. And then you already marked up your periodic table, S, P, D, and F. These are what your orbitals look like. So this is where we're moving into. We also talked about Heisenberg's uncertainty principle, that either I know the speed of the electrons or I know where the electron is, but I don't know both. And I wanted you to think of these diagrams or these areas of electrons is that if you were going to go fishing and you knew that your electron was in the s orbital, you would be fishing in that shape. If you were in the p block, you'd be fishing in the p orbitals because that's where you got a high chance of finding your electrons. Honors, you were given a scenario about the bones and you were asked to identify whose bones they were. And this causes you have to really think through this process of why you're getting what you're getting with your results. And so just some common questions here, like analysis asking you, well, what makes up the bones and what substances were present in the bone sample in your investigation? And it gives you some background information about strontium, and so you're supposed to try to figure out which bones it is. It also has you, because it says honors, it says pre-AP, calculate your wavelength and amount of energy. So you do have calculations here. And I will just remind you that your calculation is, so it has a wavelength. You're solving for frequency. You know what the C is, because C is 3.0 times 10 to the 8th. So you're going to use your equation C equals F lambda, and you're going to solve for your F. For number 5, you're going to use E equals HF. You're solving for your E. This is a constant. This is your 6.6263. Joule second. And then you have, for the previous problem, you have your F. Sorry, that's 34. Okay. And so you're going to solve for those. Okay. And then this is a real life application, because this is how on an archaeology dig, if we do find bones, we'll analyze them to try to figure out, And what's the background of these bones? Where do they live predominantly? What did they ingest on a regular basis? All that's information that we use to try to figure out where did these bones fit into our story here on Earth. Have a great one and live long and prosper.